It's my absolute pleasure, and I could talk about Mark and his project for a half hour. It's probably not what we need, but I'll give you a bit of a background on Mark. Mark is an associate professor at the University of Auckland, and he leads the Lab Animate technology group in the Bioengineering Institute. Now, Mark has an illustrious background. He's an Academy Award winner. He won a SciTech Oscar, which is one of those rigorously evaluated things that you don't get by looking pretty, but by actually doing very complicated stuff. And so Mark is here today to present some of his research. Mark has worked on quite well-known movies such as Avatar, King Kong, Spider-Man 2, and he was involved in creating some of the digital characters for these movies, and he's worked with Weta Digital in New Zealand, in Wellington, who were behind the Lord of the Rings films as well. So his talk is titled Expressive Machines Connecting Computers with People, and what he presents is cutting-edge research into learning technology and face animation technology, and the project is called BabyX, and I think Mark is ready.
Yes, thank you. So as part of the Disrupt, I had my sleep disrupted with the small time difference between New Zealand and Australia, but I'm used to the kids waking me up early, so I woke up pretty much before the sun this morning, so please excuse me based on that. So this talk is going to sort of start bridging the gap between, you know, man and machine in a way. So one of the things which I got interested in creating digital characters was, could you capture a sense of consciousness, a sense of inner life? So here's a film which was bits of a short film which was made about 14 years ago. This is about 10 years before the movie Benjamin Button, and we took a sort of a 20-year-old girl, and to her horror we made her into an 80-year-old woman. But what we were trying to capture with this thing was introspection. We were trying to capture and create an artifice which made you think about what the artifice is thinking. Now, you can do this by pretty much capturing what an actor does and then transforming that. But the thing which really interested me was, what happens if we can actually have a computer create its own inner life and express that? So essentially have a computer animate itself based on its own experience. And so I got really interested in that, and so wanted to create a lab which would basically create autonomous animation. So this is done by combining simulations of faces with simulations of brains. Now, this is actually quite a big undertaking, and it requires the integration of a whole range of things. So we really look at how we want to basically, when you think about human behavior, we're in a system. Our behavior is not just the sort of our internal sort of activities going on, but it's also the external world. It's the people that we relate to. When we learn things, we learn them from other people. So if we're going to create some sort of model, we have to think about integration on an enormous scale. It's a big, very big biological and social system that we're dealing with. Now, so the approach that we're taking is very, very transdisciplinary, because it sort of crosses biology, science, engineering, sociology, developmental science, and so forth. But we also start looking at the computer, or the thing that we're interacting with, as essentially an interface. How do we interface to the electronic world? So there's a border between man and machine, and now with the increase of technology, we're getting this border is getting very blurry. And so it actually blurs even the types of things to do with objectivity and subjectivity. What is the machine experiencing? What are we experiencing? What if we put our experiences in the machine, and so forth? So it's a fascinating area. Now, in terms of faces, so our face is our primary means of communication. So they give us, not only do they sort of tell you what's going on inside our heads, basically what we feel about something, what our intent is, but they're also critical because they're our identity. That's how we kind of separate people out and give context to our social relationships. Now, I see the face basically as an instrument, and so what we're really doing is basically building a synthesizer. Now, in order to do that, we actually need to understand what is driving the face. Now, the face is the mirror of the brain. Everything which happens on your face is as a result, which is something which has happened in your brain. And so what we're building is essentially a framework to create artificial nervous systems. So if we think about how we experience the world, we're actually constrained by our anatomy currently, how we experience the world. So we've got eyes, we get electromagnetic radiation, vibrations through sound, through our hearing, but in the electronic world we don't have those barriers. Sensory input could be the stock market, it could be a temperature sensor on an engine or anything like that. Now, we do multimodal association and connect these things together, and then we evaluate them based on our needs. So we have emotional reactions to things. So these are sort of based on what's important to us on a biological level and then also on a psychological level. Now, in robotics, this stuff comes together to create essentially behavior. But one of the areas which we're really looking at is how do you express that? And that's what faces do. That's why we've got facial expressions, is because we're trying to express our internal intents and states to other people. So we really want to think, okay, what happens if we build a framework to give machines that ability to essentially express themselves? Now, you then connect that back to the environment and you essentially create a dyadic interaction. You co-create experiences. Now, this is an example of an assembly line robot called Baxter, where they basically put a pair of eyes on top of the robot. Now, why they did that was because if the robot is thinking about like moving its arm over here, it will look there first. So what's just happened there? And if you see the robot looking there, you'll probably stand out of the way because you don't want to be hit by the robot arm. But you've inferred intent onto that robot. So this is a way that there's value in communicating what's going on in the machine to the people because it's easier for understanding. So what we're doing is basically a combination of bioengineering, neuroscience, sensing, and computer graphics. And we're taking models of the brain, theoretical models of the brain, and we're putting them together with interactive computer graphics to essentially create live, in inverted commas, computational models. So we're doing this for multiple reasons. One of them is to basically explore and embody theories of brain function. So, and this is basically by embodying some of these models which have been done in the research world. Now, the byproduct of that is actually a new type of human-computer interface technology. So we want to think about how do you actually classify what a face does if you're going to do something with it. And we want to look at what's the fundamental information which is being transferred. And so we basically move our muscles in our face to create an expression. And so to basically sort of create models of this, we built biomechanical models of the face. So what you're looking at now is a mathematical simulation of a face. It's my face because I was a guinea pig. But basically, everything that you're seeing apart from the blood vessels is part of a physics simulation. So now what we're going to do is activate those muscles. We're going to put digital activation into one of the muscles. And we create a smile out of it, but we're using the sort of an anatomy to basically create that expression. And now we can create all kinds of expressions by combining these things together. So this is like a physics-based simulation to basically create this sort of motion. Now, it's important that you do this stuff with the physical things because otherwise it starts looking robotic. So you want to get fleshy sort of motion. Now, all this is, that's a sort of background to what we're doing now. So what we are really interested in is the control system for those muscles. So we're essentially creating nerve animation. So we're combining models of the face and neural systems to drive the face. Now this has got many applications. So for example, if somebody has a stroke, you'll often see half their face will be paralyzed. But if they smile, it'll normally be symmetrical because there's different motor systems driving the face. And we want to basically model the face in a way that we have the neurological signals drive it in a way so it can be used for neurology applications, but also it can give us a sort of level of fidelity in how we're animating. Now, to drive the face, we are basically doing brain-based computing. And what I mean by that is using neurobehavioral models. So for example, how do you give a computer something that it wants to do, something, a goal or whatever? How do you give it prime motivations and emotions? So an example of so the sort of really fascinating area here is we have to look at what motivates us. And there's many levels of our motivation, but for example, a primary motivation might be my blood sugar level drops, I experience hunger, and I start seeking food. So my behavior, I'm now starting to search, but that's based on my blood sugar level. So that's an example of what I call neurobehavioral animation. Now we've also got emotional effects as well. So we have a whole bunch of chemicals racing around in our bodies, and those chemicals affect how we feel and what we do. So for example, if my stress level goes up, my cortisol goes up, and it affects how I behave, it affects how I react to things. Now, when we're doing these brain-based models, we also look at the different types of learning which are involved. Now, there's lots of machine learning techniques and artificial intelligence techniques out there, but we're taking a much more biological approach because the brain learns in many, many different ways, and we've got many sort of, some are partially redundant, others aren't, but we've got different ways that we actually learn things through the world, whether it's conditioning, reinforcement learning, association, so forth. So we want to build biological versions of these models into our computer model so that it basically starts learning from its experience. And what we end up creating is something which is a bit like the weather system. It's basically something which sort of, you never really can tell what it's going to do, but it's got characteristics. So our approach to modelling the brain is very modular. So there's a lot of pragmatism which goes into this because the brain is an enormously complex thing, so all we can really do is make toy models of bits of it. But those toy models can be quite pragmatic in the choices. So, and we want to do it as biologically based as possible. So we will use biologically based neural models where we can, and if there's something which needs to be really fast, we might use a computer vision technique or something like that. But we basically took it as this is a pragmatic system. So we want to answer the sort of basic questions about how do you decide to do anything? How do you choose what your behaviour is? It's part of the brain called the basal ganglia, which we have a model of, which is basically a crocodile is a giant basal ganglia. And this is the type of thing that you learn from your mistakes. If you do something and you get punished, you won't do it again. Some people do, but we can model that. So basically, but also this is the sort of things, you do something, you get rewarded, you increase those sorts of behaviour. So these things are running constantly in your brain as you're making choices. Now, another thing which is affecting our behaviour is essentially our emotional system. So we want to model those things because they all work on different timescales. So for example, part of your stress system is called the Hpa Axis, and it consists of a cascade of different physiological, basically hormone releases, which basically modulate behaviour. So we want to put those in the model as well. Now, when you start having a model which just reacts to the world, it doesn't know what it's going to be given. So we don't know what we're going to be given, so we basically sort of adapt to our situations. We self-organise. Our brain's a big self-organising system. Parts of it are anyway. So an example of this, here's a map of random colours and a relatively simple neural network. You just throw data at it and it just self-organises. Now, this is how we learn concepts. This is how we learn all kinds of things. So if you think about the blue area there, centre of that might be a concept, something next to it might be a related concept. When we learn sounds, it happens, words, it sounds like this. So we basically have a word and a word which sounds a bit like it right next to it. In actual fact, our brain is full of maps. There's a very famous thing called the homunculus, which is a map of the body, and they actually did on a live patient undergoing brain surgery, simulated different parts of the brain, and the patient reported where he felt it. Now, these maps are actually starting to come into technology as well. So the visual system has many hierarchical maps. Now, Google and Facebook now, there's a lot more sort of use of a technique called deep learning. And what deep learning really is, it's basically a bunch of hierarchical neural networks, which is very biological in its nature. So we build these types of models in as well. Now, we also, when we experience our life, we experience it specific. So when I'm talking about different types of memory, you've got general memory, but you've also got episodic memory, which is sort of remembering specific events. So we can model these types of things too. This is part of the brain called the hippocampus, which is like the brain's librarian. It's like you go, oh, I'm thinking I need a book by, I can't remember the full name of the author, but it starts like that. The librarian goes, oh, you mean what is it? And it's stored here. So the brain has a part which automatically does that. It creates a whole experience from bits and pieces. Now, you can take these models and kind of look at theoretical basis. So they look at the sort of construction of these neural circuits, and that gives a basis for a theoretical model. So to show you one of these in action, here's a model here where if you look at on the right, we've trained this on a sequence of numbers. So now I'm going to give it a partial 1, and the network is basically imagining the sequence of numbers. It's like it's remembering a phone number. Now this is really important because when we plan something, we imagine the future. So one concept of imagination is that it's memory of the future. So these are types of things we can have computational models which are biologically based, remember specific things and fill in the dots. Now we also have causality detectors built in, and we associate things, we attend to different things, we put things in different contexts. And so when we're conscious of something, we'll be thinking about certain things, and then we might flip our attention to something else. So we can model these types of things as well. So there's a lot of work which has been done in the literature to build these computational neuroscience models of the various aspects of the brain, but they haven't really been put together, and they haven't been embodied. So what we've been really looking at is how do we do that? And you know, they're enormously complicated, these models. So we basically built a system to build systems, which we're calling brain language. And it's basically a Lego system for the brain. It's a Lego system for building neural networks, processors, attaching them to sensory devices, and critically, we also attach it to animation. So we're incredibly sort of intimately linked with computer graphics to be able to visualize what's going on. Because when you get these complex things, you need a very visual programming system to do this. So our language BL basically combines a whole bunch of different things from biomechanics, animation to neural networks, so you can build these models up. And so how does all this stuff come together? So basically, you know, we can build a model. We can start with a 203 neuron nematode, but that's not that interesting. So I'm going to show you how to make a baby on. Please turn the cameras off for this bit. But basically, with the baby, it's like, what's the metaphor for this? How do we kind of start with this? Now, we don't want to deal with all the complex adult baggage, so we'll just start with the baby. We'll start simple and look at things how they kind of develop. And so here's a real baby. So it's a little stereo capture. And now here's the real baby having solid food for the very first time in its life. It's having a fundamentally new experience. Now, everybody gets that. Now, what happens if you have a machine, when it learns something, do that? You start getting connected to that machine. Now, if you think about the world that we're in of big data, this is going to become increasingly important. Oh, my computer doctor's just said I've got whatever. You're going to want to interrogate that answer. You're going to want to be connected to those decision processes which are going to affect our lives. So this is something which it's a barrier that we kind of have to pass. We have to essentially address this. So this is more baby stuff. This is, building 3D baby, biomechanical baby. And then we activate the biomechanical baby muscles, because real babies won't do what they're told. And then we start putting in the different neural models to drive this. So, you know, we're basically building a model up bit by bit and adding the various features which drive the behaviour. And so the interesting thing about some of the models that we put in is they're actually developed to study particular diseases. Like one of the models that we're using is developed to look at the effects of dopamine, for example, on Parkinson's and Huntington's disease. So we put these things in the model, and we can actually play around with the parameters and things like that and sort of simulate those effects. So we're not actually developing the neuroscience for that, but we're using other researchers' models. And so if I put all the pieces together, I'll just fire up the baby. So let's see. Now, I think this is okay. Okay, so what it's doing at the moment is it's compiling its brain. So it's basically starting off kind of blank slate, and you know it could wake up grumpy. I don't know what it's going to do. So we'll just see. So we built the mock. Okay, there she is. She's very. Oh, she is a little bit. Hey, sweetheart. So she's she can see and hear. So she's listening. If I make a loud noise, she'll get a fright. So all these types of things we can zoom right in and have a look at her. You know. So she's listening to me. I'll smile at her. Hey, sweetheart. Now I can also now we can take a look at kind of the types of things that she's seeing here. So if we zoom in here, you can kind of see where she's looking. So if I walk over here, hey, looking at me, hello. Hey? And now, what we're seeing up here is we're seeing different neuromodulator levels. So we've got all kinds of things modelled like oxytocin here. So we've got all these are sort of modulators of behaviour. Now I'm going to essentially abandon the baby now. I'm just going to, she'll start getting stressed and she's going to start looking around for me. But if you look at where the sort of mouse pointer is, you'll see the cortisol levels will start to rise. So we've got a sort of a dip in oxytocin. And we're going to, she will start getting a bit upset because I've essentially abandoned her. And this is like real babies. If you walk away from them, they start getting kind of stressed. So she's, it's okay, sweetheart. Oh, it's okay. Hey, stop crying. Oh, yeah, that's good. Good baby. Now with in terms of the online learning things, so you've all heard of like Pavlov's dog. This is a type of thing called conditioning. So if I give her an unconditioned, a conditioned stimulus, a bell, it doesn't mean anything. But now I'm going to pair that with something. Okay, hey sweetheart, the bell is good. You like the bell? Yeah, the bell is good. Yes. Okay, so now I'll just do the stimulus again by itself. Okay, so that's like Pavlovian learning. So this is one aspect of how we learn. Now, if we start doing, let's have a look at another thing. So we start looking at kind of where her eyes are looking, and you can kind of see that she's looking at motion. She's looking at things that she gets interested in. She gets bored. Now, I can even basically, what I'm going to do now is I'm going to say, bad baby, bad, 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 bad. Now she's deliberately going to avoid me. Hey, I'm over here. This is like a real child. If they're overstimulated or they're sort of whatever, they want to avoid you. So you can do all these types of things. Now what I'm going to do is remove the face of the baby to see what's running behind it. Now this is running live. Now this is where we've taken the neural networks and we've put them on computer graphics onto the neuroanatomy. So as these eyes are moving around, you can actually see the nuclei in the brainstem which are driving the eye movements. So if we have a look underneath the brain there, we can kind of see the optic pathway. I'm going to spin around here, and we can zoom in and see the visual cortex there. So we've mapped everything in the appropriate anatomical places. And now we're going to zoom into the brainstem. So this is the part of the brain called the superior colliculus, which is what sort of that's your almost like your theatre of the world. This is where sensory events happen relative to your body. So if an explosion happens over here, I'll look over here. But we can kind of see those things competing for attention, and these things are driving the eye muscles, which are driving the eye movements. So now we can come out of this, and we're going to start looking at a thing called a thalamocortical loop. So I've got essentially up here where the mouse is, you can't see because it's dark and so it needs light, but basically this you can't really see it on this, but there's a little thing firing here, and when we essentially have an idea, that idea builds up and it either becomes something that we do or it might get shut down because it's a really bad idea. Now this in the motor system is actually affected by dopamine. So if I bump up the dopamine levels, so I'm going to do a you should see, I can't. Okay, here, see the green thing lighting up here. We're now getting too much feedback into the system, and this is what happens in Huntington's disease, because basically every muscle starts activating at once, and it's called chorea. Now in Parkinson's disease we get the opposite, so I'm now going to bump down that dopamine, and now what happens is the pathway's shut down. And it means that they want to move, but they can't. And so we can also look at this, because of the way that we've mapped the model onto all the graphics, we can look at this in other ways. So if we look, here's the baby. Now let's look right into her pupils here. Okay? Now I'm going to give her, essentially, I'm going to boost her dopamine levels. This is equivalent of giving the baby cocaine. Now she's also starting to blink faster too. Now these are clinical markers of how the basic clinicians look for these types of things. So you can do, this is the whole thing about kind of combining the internal forms of behaviour with what we can do. Now we've also been basically teaching baby to read. So we've got her book of first words here. So I'll come out of here, and so we'll zoom into this so that you can kind of see what she can see here. Okay, now I'm from New Zealand, so I've brought a sheep with me. So now I'm going to turn up the volume. Okay, sweetheart. Okay. Right, okay. What's this? What's this? What's this? What's this?
Sheep.
Good girl. Now, see if she can read the word. Okay, sweetheart. What's this? What's this say?
Sheep.
Good girl. Now we can show her something else. Clock, for example. Okay, here we go. What's this? What's this? What's that?
Clock.
Good girl. Okay, so we can do all these types of things. So she can kind of read words, recognize pictures and things like that. And now she can also, I'll show you, this is one of the things which takes a longer time, but this is one of the basis of empathy. So this is essentially learning to imitate, an expression. So here what's happening is, as the caregiver, I'm copying what the baby's doing. Okay, so she's doing something, I'm copying it, but she's associating that copying of behaviour. Now this is, what she's doing with her face is essentially called babbling. It's like doing random movements, but that's how your brain starts associating the, now she's now copying me. She's learnt the association. Now everything that you're seeing on her face is generated live by neural networks. So all the expressions all combine together through the appropriate pathways to produce those expressions. Now we can also do things like we've attached her brain, she doesn't know, but we've attached it to the game Pong. So she's actually controlling that bat with her mind. She doesn't know this, so she's not very good at it. But she starts getting a reward every time she hits it because something new happens. So over time, she starts being able to control the bat. And this is just like learning to control your arm or something like that. Now, the other thing which is kind of fun with this is I took it to my daughter's school, and you can start seeing what is a computer experience. So here's kids interacting with it, and she remembers things which, significant events. So there's a bug there, and that's why the faces are blue, but I liked it, so I just kept it there. But it's a sort of a fun type of thing. Now we can also, it doesn't just have to be realistic faces. We can actually put all this stuff on a character. So, it's basically the idea is that the signal, the communicative behaviour is the same. It doesn't matter what it is. We're used to faces, but we can transmit these signals through characters. Now, we're also doing sort of other applications of this technology. So at the moment, we're working on an avatar for the airports. So this is like a baggage checking system. So what you're seeing on the right is a real-time screenshot of the avatar. So she's going to be extremely realistic. You're going to be able to zoom right into her eyes and everything. And she'll be kind of guiding you through that process. So there's a sort of this is this sort of way where we're using human type expression and behaviours to sort of help the communicative gap. Now, so that's kind of it, and I've got a fantastic team, so I want to thank them because it all wouldn't be possible without them. And I'm not sure how long I've taken, but I can probably take some questions. But thank you.
Wow. Can I talk to her later?
Yeah.
Mark, this is great. I mean, pun intended, but that's mind-boggling. And that was live, right? So that wasn't pre-recorded.
No.
We need to point that out, and also that this is serious research. So we were a bit worried earlier with the ABC in the room that we might, mistake this for a gimmick. So this is really impressive stuff, and thank you so much for sharing this with us. At this point in time, we are going for lunch, but I'll just open it up to anyone for questions. And also, Mark is going to stand here for the next half hour if someone wants to come up. And I'm just selling you, right? So I didn't ask him.
No, I am happy to ask, because at some point I will want some food.
Yes. So yes, please.
So you've used humans to help establish this, but have you used it vice versa to help neurological diseases and stuff like that?
Yeah, so that's an excellent point. So what we're doing with the adult model is we're actually doing it in collaboration with the Department of Psychology, and we're going to be essentially creating psychophysics stimuli. So these are types of things where the face is such a potent sort of potent force in activating brain activity in different areas, because it's one of the most important things that we do. So that by being able to control the stimuli and then measure the results of that, we can start seeing, what's happening in different areas. The other thing is, you know, we're really kind of putting this out there. This is what I kind of think of as a sketch. We're kind of sketching out a whole bunch of different technologies. So it's all about integration at the moment. And so we're wanting those people to come out of the woodwork and essentially work with us to build up the different things. So every model that we're using in there is replaceable. So they're all, that's why we've made things very modular. It's like, okay, we've got a model of this part of the brain, and at the moment it's a placeholder. You know, it's the best that we can do at the moment, but if somebody's got a better model, we just swap it out. And that's the sort of idea. So, you know, there's everything in this, from Botox, you know, you can sort of work out where you want to inject something, to different neurological conditions. And so, but a lot of the science for these things is really not known too. So in those cases, you know, we basically have to connect the dots through a black box because we just don't know that. But we're trying to basically go, okay, if you build this big system, like, you know, put all these pieces together that we've currently got, what do you have? You know, where are the points which need filling? So really we're kind of doing this to put it out there. And I should say that as part of this, we're really looking to collaborate with people, whether it's researchers, businesses, you know, whoever basically on this project, because it's all about integration. It's about psychology and science and, you know, applications too. So.
How does it compare with the artificial intelligence research such as the IBM Watson?
Yeah, okay, so that's a great question. So I was just talking a couple of weeks ago at a thing called a cognitive computing forum, and there's people from IBM Watson and so forth there. So IBM Watson is a hypothesis generator, and what it does is it goes through thousands of hypotheses to basically, you know, create a response. Where we've kind of looked at pitching this is as we can connect it to that. We can connect this to Google, to IBM Watson, or to whoever else. Because it's essentially, you've got to have, how do you take big data and things, hypotheses and things represented by IBM Watson, and connect that to the audience? And so one of the things which was key in that conference, and a repeated theme, was the importance of interrogating your big data. The importance was that you have to, you know, you've got a machine making a decision for you. Now typically you'll have a data scientist basically who's an expert in the field go, oh, this data means this. But as this starts becoming more ubiquitous, we're going to need better tools to sort of access that data. And you know, this is where the power of facial processing and so forth starts coming in, because we can sort of put things through multiple channels. We can, and also the visualization. So I mean, it's really in its infancy, but we need to communicate with the maximum dimensions that we can.
You said you've used reward systems to train her to learn what to do with that Pong example, but what is the reward for?
So she gets a dopamine hit. Basically.
So it's literally increasing a dopamine.
Yeah, no, but that's exactly how it works. And so we're based, a lot of this stuff's based on behavioural neuroscience research, so that they've basically, you know, measured sort of rats and monkeys and things like that, and they do get these dopamine spikes. And it turns out that the dopamine spike affects the plasticity of the network. Now, what that means in terms of a neural network is that affects how it learns. And so nature's got these ways of providing perfectly timed training signals. Where does ethics? That's funny because we're so we are actually in a related study. So we're actually doing collaborations with developmental psychologists, and that's where we're studying infant caregiver behaviour, because what we're trying to do is look at the essence of communication. What are the building blocks of how we learn anything? So all that thing is very ethical, because that's really basically building models of communication. Now on the digital model, then we might need, because it's what's really interesting with this model is that when I do the reward, I could also give her an electric shock, right? And everybody in the room would disapprove. But it's not a real thing. But we feel it. And so this is the sort of boundary that we're crossing. So it's like, you know, I would be bad if I pressed the electric shock button instead of the reward button. And so this is a bizarre thing, because we will have to deal with this at some point in the future, because we're going to get to the point where if a machine has, and essentially one of the things we're trying to do is build a machine that you don't want to turn off, because as that baby, as a digital baby, basically goes through life and it learns from experience. One of the reasons that we value life is that we're essentially valuing the experiences that people have. As a life gets older, it increases in its all the things, the richness that it's had, and so it's a very valuable thing. Now, with a computer thing that's a shared experience between computer and people, it's kind of encapsulating that, and that's something you don't want to throw away. So there may be some ethical sort of issues there, that this is an artifact which has been created. It might be like destroying I read something recently about this new type of thing is like an artwork, but it's putting the work into the art. The art has to work. So I think it's this is a brand new sort of area. So yeah, I don't know. So that's yeah. This is I always get this question. I call it the Skynet question. So basically that's the reason that we've made it a baby, so nobody will see it coming.
Mark, though, I want to tie in with that because you presented this previously in other contexts, and the baby was younger.
Yeah.
So is she growing up? Is that your kind of versioning?
Yeah, I'm actually. So this baby looks just like the real baby equivalent. The real baby's a bit older now, but we've been sort of growing her in ages. But one of the things is I will probably stop growing the digital baby at some point because I don't think it's right for the real baby to have her cyber clone. But it is an interesting thing because if I ask my real daughter, I say, "Who's that?" and she says, "It's me," and then we fly into her brain, and then.
So the real baby, we understand, can learn some words and so on through strengthening those neural networks. But as this baby grows, for example, do the ocular muscles get stronger, or do you have to make the ocular muscles stronger?
Yeah. So in this case, all the muscular system, we haven't had to do that.
Right.
So
only the cognitive system.
It's what we put into the model. So if we wanted to essentially. Yeah, but there's a point where the reason that we're doing this is essentially create an emergent system. So at a certain point of organisation, then things start self-organising. So there's.
I was going to say, at what stage does it start to self-organise in the muscular system as well as in the cognitive?
So the muscular system, we haven't put that in terms of self-organisation. Right. Actually, no, we have a bit because that's the sensory motor learning. So it depends what you mean. Like if we put in a physiological model of how the muscles actually grow, that's an entire other level of computation. It is actually studied in my institute on computational physiology. However, what we are modelling is the sensory motor system. So we're modelling how the brain controls the muscles and how that develops.
Do you turn her off every night? Are you afraid to leave her on overnight?
Actually, what we're doing, so what we're going to do with her at night is she's going to dream. So she's going to basically process the day's activity, and you'll be able to come and watch her dream.
Sorry. Another question here.
Maybe one more question, yeah?
Yeah, hi.
With the emergent... Is this on?
Yeah, it's on.
Okay.
I can hear you.
With the emergent learning system that you've currently created, does that extend to conversational learning and interaction, or is it just pattern recognition and input?
So these are all layers of a hierarchy. So if you think about how we learn in these building blocks and we make layers and layers of them, and they're kind of related to context. So we might learn a word, for example, but when a baby hears a word, it'll be in a context. So it might first understand a sentence. So think about if you're learning a foreign language, you'll probably learn phrases before you learn the actual word in order to get around if you're actually immersed in the environment. And so what you're actually learning there is context. Now, if you take hierarchies of context, you end up getting meaning eventually, because when you get to the level of understanding something, you've got an invariant concept of the world. In other words, like I see a dog and I've got a memory of a dog and I see lots of different types of dogs. I'll eventually have a dog which is independent of the things that I learn. But the first time that I see a dog, it's a new thing. So those are, so that's what you've asked is a very deep question, and we're trying to build a machine which can do that.
So following on from that then, so given the input rate of learning at the moment is restricted to you.
Yeah.
In theory, you could give this another computer or a system or the internet or something to rapidly accelerate.
That's what we're doing with the adult model. So the adult model, we basically can connect to ontologies and things. So with the baby model, so this project's got multiple sort of avenues. What I'm really interested in this is how do we learn anything at all. That's my real sort of focus and interest. But on the other side of the coin, we've got a technological system where with the adult model, we're going to give her prior knowledge. But then she'll learn given that prior knowledge. Yeah, and the thing is that you can, if you plug it into Google, you've already got a knowledge base, right? So it's like, so essentially, but it's those types of things where you're going, but it's also how do we interact with Google? So you've got things like Siri, which are a part-way step, where you've got essentially, you know, we're putting a face and expressions and interactivity on top of a Siri in a way.
Well, Mark, one question is, we learn it, when we grow up, we learn the word by holding onto it, latching onto it, using it with our bodies. We have to learn sense of gravity by learning to walk and all of that. How do you account for the fact that BabyX doesn't get the experience of bodily being?
Yeah, that's a great question. So there's a couple of answers to that. So that is a fundamental thing, and that's one of the things that people do in developmental robotics. They actually build robots which experience the world in terms of all its physical forces. For our baby, it's like she's looking at the world through senses, but those senses can be anything. So if we did put, you know, she could have senses like. So one of the things that we're doing, we've got a project on this, is we're putting the baby on these little robots which drive around. So she's actually going to have multiple senses, and they're all going to be exploring. So she's going to be exploring the world like an octopus. So yeah, so we can do those types of things, and then you start adding on more and more technological integration, and so there's all these areas to explore. But
are you collaborating with any philosophers on this?
Actually, I've spoken to a couple of philosophers, but I'm very interested in the philosophy of this. I mean, this, in a way, that's why I showed those slides at the top, and sometimes if I have a longer talk I start with, you know, slides. Yeah, yeah. but really it's a philosophical it's a philosophical study in a way at its heart.
Yeah, and it's really good. It gets us all thinking on our own different kinds of ways, and I think it was truly disruptive. So thank you so much for coming.
Sure.